Last video we talked about the ideal characteristics of an amplifier, which we came up with right here, and then right at the very end of the video I said, well, there's this practical circuit that you can build called an op-amp, which is short for operational amplifier, that for all practical purposes has these ideal characteristics. So I want to start with what this circuit looks like. See, here's a simplified schematic electrical drawing of an operational amplifier. So you can see that even though this is simplified, it's still a fairly complex circuit. It contains about a dozen or so transistors. You can see a couple of diodes, and you know, there's actually more components. There's some capacitors that have been left out of here. Now, fortunately, in this class, we're not going to analyze this circuit down to a component level. We're just going to look at it more as a black box in our analysis. But I did want to point out a few things in this detailed diagram. First of all, notice that the operational amplifier does have two inputs, and one input is labeled with the minus and the other input is labeled with the plus. Now, the minus and plus here have nothing to do with the polarity of the voltage that you connect to these input terminals. You can connect positive DC or negative DC to either one of these inputs, as well as AC signals. All the minus here represents is an inverting input, and we'll talk about what inverting means later. And the plus here just means that this is the non-inverting input. Okay, and again, we'll talk about what non-inverting means later. So there's two inputs, and there's one output, you can see over here. And then look, there's a plus V and a minus V. What the plus V and minus V are, those are the DC power supply voltages that power these transistors. So you may recall that in a common emitter amplifier, a common emitter BJT amplifier that we looked at earlier, there was only one source on the output side and also one source on the input side that were both supplying positive DC voltage. But this circuit has a negative and a positive power supply. So what that means is that your output can be negative as well as positive. Remember, with the common emitter BJT amplifier, because of the only sources being positive being supplied to the circuit, your output could never be below ground. Okay, it could only be between ground and the VCC amount, which was one of the power supply values that was on the output side. Okay, but what we'll see here with op amps is that the output can be negative as well as positive. Now, a few more basics about op amps. Here, this is the circuit symbol for an op amp. You can see it's a triangle shape. Here VA is the voltage to the non-inverting input, and here VB is the voltage to the inverting input. And here's the output. And when you just have an op amp without anything connected around it, and you'll see that the majority of op amp circuits will have some component connected between the output and at least one of the inputs. But in this case, where you don't have anything connected around the op amp, you just have the op amp itself, the output is just equal to the open loop gain that we talked about, the constant, times the difference of the two input voltages, so VA minus VB. We'll see later in the course that this circuit has an application. One drawback of this particular way of using the op amp is that it does have an unstable point, the unstable point being where V out becomes unstable, but we'll talk more about that at a later time. Okay, right now I just wanted you to see the circuit symbol along with this expression here. Again, when there's nothing connected around the op amp, we're going to be looking at various common op amp circuits, you know, 5 or 6 different circuits where we have various components connected around the op amp, and we'll see how we come up with what V out equals in those cases. Now, just like there was a limit on V out for the common emitter BJT amplifier, there's a limit on V out for the op amp, and I mentioned this just a few moments ago when we were looking at the previous diagram of the circuit schematic for the op-amp circuitry, and that's the limit on V out is that the output voltage has to be within the two power sources that we're supplying to the op-amp. So V out has to be within plus V and minus V. In fact, there's a term that EEs use, okay, rail. Each one of these power sources is referred to as a rail. So plus V is the upper rail and minus V is the lower rail. So V out has to be within those rails. See, if V out was outside of these power source values, that would be a violation of conservation of energy, because again, you can't get more out than what you're putting into the system, okay, putting into the op-amp circuit. Okay, one other diagram I want to show here, and this is useful particularly for those of you that are taking the lab that goes with this course, but here's a pinout diagram for the op-amp. Op-amps most often come in integrated form, okay, and in the lab that goes with this course, an op-amp, a 741 op-amp, which is a very common type of very common op-amp, is used, and this diagram shows the pins and how it corresponds to the op-amp circuitry. So you can see here, there's the op-amp symbol we just talked about, and the inverting input for this op-amp is pin 2, the non-inverting input for this op-amp is pin 3, the output is pin 6. You would connect the positive voltage source to pin 7 and the negative voltage source to pin 4. And you got to be very careful when you're hooking up these power supplies to the op-amp chip, because if you were to accidentally, or for that matter on purpose, connect these backwards, okay, put the negative voltage to pin 7 and the positive voltage to pin 4, you will damage the op-amp. It will overheat, and you know, if you have it hooked up backwards long enough, it would actually start to smoke and disintegrate. So you'll physically damage an op-amp IC, and for that matter any IC, if you hook up its voltage backwards. ICs are voltage polarity sensitive, like we talked about earlier in the course when we talked about the voltage polarity protector using a diode. Now there's two other pins, offset null, okay, 1 and 5. I'll talk more about what offset null is in a future video. And then notice here pin 8 doesn't have any connection. And the reason pin 8 is there, even though it's not connected to anything, is just because an 8-pin package is a standard type of IC package. You know, they don't have a 7-pin standard, so it would actually cost more to manufacture a 7-pin package. It's cheaper to manufacture an 8-pin and just don't use the 8th pin. And then just like any component, a op-amp IC does have maximum ratings, and you can see some of them here. You don't want your magnitude of either supply to be more than 18 volts, otherwise you could damage the chip, and your input voltage is limited to a magnitude of 15 volts also. Alright, so that's some basics on op-amps. The next handful of videos, each video we're going to look at a different common use of an op-amp.